Okay, guys, good morning. It is almost 9. Okay, 1 minute to 9. All right, so I can start probably. So first of all, the first midterm exam is going to be next week on Thursday, right? You can look at the course policy. The dates are there, and I usually try not to change those, the exam dates, right? I think there was only once, because that semester we had so many snow days, so I couldn't, I had to postpone the exam, I remember. All right, so the exam will be on Thursday. All right, so I need to think about the exam review session. Maybe it will be tomorrow on Friday in the evening, right? I will inform you, right? I need to sort of plan a little bit more. Then, all right, I want to ask you, do you have any classes on Thursday at 8 a.m.? Because if you don't, then we can start slightly earlier, and I can give you some extra time so that you can scan your solutions and upload them to Gradescope, right? Otherwise, I'll have to come up with something else, right? So if you don't have 8 a.m., if you do have 8 a.m. classes, just please send me an email, right? So I will know. Right? Otherwise, if you don't have classes at 8, then it will be easier to organize the exam, right? Because usually I give 50 minutes for the exam, and then you still need about at least 10 or 15 minutes to scan your solutions, right, and upload to Gradescope. Right? So we need to find that time. Okay, so that's about the announcements. Again, physics department organized the tutoring center for you, right? So information about the tutoring center is in the Blackboard, so you can go there and see. And of course, links are there, and the code is there also, right? So you can see all that. All right. Yeah, that's it. And now let's go back to the class material. So where we are. So in the previous lecture, we started making a big turn, right? So up to that point, we've been using all the time vector quantities to describe electrical systems. We use the electric field and the electric force. And again, they both vector quantities. Again, nothing wrong with vector quantities. They're great, but it's tedious, even difficult to work with them. Of course, it's much, much better to work with scalar quantities, right? So we decided, let's try to make our life easier. Again, there's no real desperate need to do that. But if you have a chance to make your life easier, why not? Right? So that's the logic, and we decided, okay, let's try to replace these vector quantities, two vector quantities, with two scalar quantities. But again, very important, all of the quantities must describe exactly the same thing. All right, so in the previous class, we replaced electric force, which is a vector quantity. I just see that there's some activity in chat, so I just checked. Maybe I'm muted or something, right? And this time I removed the sounds. When you chat, I don't hear that. So in the previous class, we replaced electric force, which is the vector quantity, and which describes interactions between charged objects, right? And we replaced it with the electric potential energy. Right, so, and again, potential energy, it is an energy which describes interactions. So you see both of these quantities, vector quantity and scalar quantity, describes interactions. So they're describing exactly the same thing, right? So we're not using two quantities which describes apples and oranges. No, the same thing, interaction. So that's what we wanted, right? So we replaced vector quantity with an equivalent scalar quantity. All right, so, and we practiced in our recitation classes, right? And now we will have to deal with the second quantity, right? So I created this table. It's nice, right, to have something like this. It gives you a better picture. So what do we have here? First column, vector quantities, which we want to dump. In the second column, scalar quantities, which we want to introduce, right? And here, the first set of quantities, describe interactions. You remember force, and if the force is conservative, we can introduce the electric potential energy again. That's what we've done in the previous class. In this class, we will have to deal with electric field. So we need to replaced. We need to replace the electric field, which is again vector quantity, difficult to use it, all that blah, 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 right? And so now we want to introduce something which has a scalar nature. Right? But look, how did we introduce electric field? E, you see the electric field, right? So we took vector quantity which describes interactions, force, and divided it by the value of the probe charge. Guess, how are we going to introduce the scalar quantity, which is equivalent to the electric field? In exactly the same fashion. So we will take now scalar quantity which describes interactions. Here we had vector quantity which describes interactions. Now we're going to use the electric potential energy and divide it by the value of the probe charge. And that will be our new quantity. So we're going to introduce this new quantity V. You see, scalar quantity which describes interactions, potential energy, divided by the charge. And here, electric field was introduced in this way. Vector quantity describing interactions divided by the probe charge. You see, similarity, direct similarities, right? Okay, so now we introduce this new quantity. It's a scalar, all right? And so now, of course, we need to give it a cool name. Right? It's very important to name it properly. And electric potential. And yeah, it sounds good. I agree. Right? Sounds good. Or just sometimes people just skip electric, just potential, because we live this in the world of electricity, so everything is electrical. And later on will be magnetic stuff also. So the electric potential. So this new quantity. And yeah, now, so we introduce new quantity. What's next? What about the units? You remember when we introduced the electric field, we didn't give a special unit. And I explained to you, justified, right? Because electric field, yeah, it's one of the fundamental quantities in physics. It's ridiculously important, right? But still, it doesn't have a special unit. And the reason is because it is used mainly by physicists, right? Engineers who do research, right? But in our everyday life, technicians, engineers who just do sort of down-to-earth work, they don't use the electric field. Or they use it, but not very often. So as a result, there is no real need to introduce a special unit. But what about the electric potential? Electric potential we use in our everyday life almost every day. Look, I have a battery, right? And if we didn't introduce the special unit, every time I would have to tell you, okay, I need 1.5 joules per coulomb battery. I need 9 joules per coulomb battery. I need, 125 joules per coulomb. It's annoying, right? It's annoying. It's very impractical. So in order to simplify, since it is used a lot, all right, in order to simplify our life, it's natural to introduce the special unit, volts, right? Volts. So instead of pronouncing every time joules per coulomb, volts. But of course, on the other side, of course we can introduce the special unit for each quantity, but then there will be a big pile of different units, and it will be difficult to remember all that. So every time you see physicists and engineers, they try to keep the balance, right? So that there wouldn't be too much of special units, right? So that it would be difficult to remember. But also at the same time, we try to introduce special units only for the quantities which are used a lot. Right? So electric potential, yeah, it is used a lot. So it makes sense to make our life somewhat easier. Right? Okay, so volts. So that's the general definition of the electric potential. So you can apply this definition for any system, right? So of course, we're going to apply it today for 2 electrical systems: parallel plate capacitor and point charge. Our systems which we will use pretty much Okay, a lot, a lot. Okay, now, after introduction of the electric potential, now practical situation in order to introduce a very important formula which we will use a lot. Let's imagine this situation. So some electrical system creates an electrical aura over here, right? It doesn't matter which creates, but we know that this area is filled with the electrical aura, which can be described using either electric field or now we introduced the electric potential. So let's assume that we know electric potential at every point of this area, right, or volume, whatever. And now let's imagine that you have some charge flying in your experiment, right? Let's say some electron or proton flies through your this electrical aura. And so the question is, how can we find electric potential energy, which we used in the previous class, right? Electric potential energy. Of course, this charge is going to interact with this with the system which creates this electric aura, right? Of course, there must be some potential energy. So the question is, how can we find electric potential energy? Very, very simple. That's how we introduce the electric potential. V equals U over Q. Just solve it for U, which is the electric potential energy. So U equals Q times V. And that's a formula which we have to use in order to find the potential energy of this system. For example, let's say you want to apply energy approach like we've done in our recitation section in order to find, for example, velocity of this object at some moment of time. So you'll have to use conservation of mechanical energy and you will have to find the potential energy, right? So yeah, that's it. Q times the value of the electric potential at the point where the charge is at this particular moment of time. And it's very similar to what we introduced in the second lecture of this semester. You remember? So if you have a charge exposed to the electric field, so how can we find the electric force? QE. And here, QV, right? So similarity, lots of similarities, right? I can say in exactly the same way we can find, right, the electric potential like we used to find the electric force acting on the charge Q. Okay, so this will be used a lot in this semester. Whenever we have to use conservation of mechanical energy to find motion of some electrical system, right? So every time we will have to use this. Okay, so now let's write down the expressions for the electric potential of a parallel plate capacitor first, and then of a point charge, because we will use this system, as I said, a lot. Right. Okay, so let's start with the PP capacitor, with the parallel plate capacitor. Again, so some negative electrode, positive electrode, electric field from our past, right, pointing from plus to minus. But now we want to write down the expression for the electric potential, V. Right. Okay, so we will take the probe charge, you see it, probe charge Q. Right. And of course, let's introduce coordinate system like we've done in the previous class, you remember, right? The origin is at the negative electrode, right? So S equals D, the spacing between the electrodes is D. Right? And you remember I derived in the previous class the expression for the electric potential energy, right? Using the whiteboard, you remember I spent some time, like 10 minutes, deriving it. And I derived that. Electric potential energy equals charge times the electric field times the distance from the negative electrode. And you remember, whenever you introduce the electric potential energy, you need to show where is your reference point. In this case, the reference point where S equals to 0, which is the negative electrode. That's our reference point. Right? And of course, you need to remember that S is measured from the negative electrode. It's very important, right? Okay, so now what do we have to do in order to introduce the electric potential? So here's the definition. V equals U over Q. Basically, you just need to remove the Q. That's it. As a result, that's the formula for the electric potential inside of a parallel plate capacitor. electric field, which is constant, you remember? Electric field inside of a parallel plate capacitor is constant, times S. S is your basically variable distance from the negative electrode. So as a result, this function is linear. So we have linear dependence of the electric field, electric potential, of the electric potential. Okay, all right, and again, so whenever you work with the electric potential, it also has the reference point. Of course, you should mention also where is your reference point. And a reference point is at the same point where the reference point of the electric potential energy. In this case, the reference point is at the negative electrode. Okay, so, all right. Yeah, and as I said, so the electric potential of the negative electrode, 0, and then it grows linearly as you move closer to the positive electrode. And of course, maximum value is at the positive electrode. And I took this picture from the book. Right? So you see the book, the author overlapped this sort of picture of the capacitor with the plot. You see V, electric potential vertical axis versus S, right? And you see this green line. So electric potential grows linearly, as I told you, right? With 0 value at the negative electrode and maximum value at the positive electrode. Okay, so that's the electric potential over parallel plate capacitor. But you also heard and know about the electric potential difference. Basically, potential difference between 2 points, for example, point 1, point 2, find delta V. Right? We will use, of course, a lot. All right, so now let's find the formula for the potential difference across a capacitor, which is quite simple, but we will use that formula from time to time. I think in 2 or 3 places, in 2 or 3 lectures, I will use that. I will tell you guys, you remember that lecture, we derived that formula, and we will use it. So it's very simple. So potential difference across the capacitor. Delta V, C stands for capacitor. So that's the potential difference at the positive electrode, right? At the positive electrode, minus V minus, it's a potential. Okay, I said potential difference. No, potential. Electric potential at the positive electrode minus the electric potential at the negative electrode. So this is E times D. S equals to D, so ED. And minus 0 because the electric potential at the negative electrode is 0. So the potential difference is the electric field times the distance between the electrodes. Again, as I said, we will use that a few times in the future in this semester. Right, so that's the electric potential inside of the capacitor. Now, next, electric potential is not visible, right? Like electric field, right? And of course, it's very useful to come up with some lines which can be used to visualize the electric potential, like we've done with the electric field. We introduce electric field lines, and then in the future we will introduce magnetic field lines. Now we need to come up with some lines which can be used to visualize the electric potential, so that you can look quickly at the picture and you can tell, okay, here it's larger, here it's smaller, right? So it's some quick analysis of the electrical system, right? Okay, so which lines can be used? Look, what if we step away from the negative electrode, but by small distance, let's say this distance, and look at points, at all points at the same distance from the negative electrode. Let's say here you'll have 1 volt, 1 volt, 1 volt, 1 volt, because the electric potential depends only on the S. Electric field is the same, right? So each point on this line are at the same potential, electric potential. So let's use lines like this to visualize the electric potential. And we call them, since electric potential at all those points exactly the same, let's call them equipotential lines. So these lines are used to visualize the electric potential, right? Okay, so now next, I took this picture from the book, right? So you see negative electrode, positive electrode, and two equipotential, in this case, surfaces are shown because it's a three-dimensional picture, right? So you see, this surface parallel to the electrodes is at 0.5 volts. So each point on at that surface is at exactly the same potential. So we can call this equipotential surface. This surface again parallel to the electrodes at 1 volt. So equipotential surface. Or if you look at the sort of like a cross section, right? You will, okay, so it's electric field, right? Capacitor. If you look at the cross section, you will see this is that line, that surface. This line represents this surface. Then, of course, maybe this surface will be represented by that line, and you can, of course, draw even more lines like these. Again, equipotential surfaces, or here we can say equipotential lines. Okay, what's the angle between, you see the electric field from plus to minus and equipotential lines? What's the angle between these two sets of lines? 90 degrees. It's not by accident. It's not just true for this situation. No, it is true for any electrical ore. So if you have electrical ore and if you draw properly your electric field lines and equipotential lines on top of that, every time the angles between these two sets of lines must be 90 degrees. If it's not true, there's something wrong with your picture. It doesn't matter how complicated your electrical ore is, all the time the angle between the equipotential lines and the electric field lines must be 90 degrees. Next lecture, I think next lecture, I will prove that. Right? So 90 degrees.
I have a quick question.
Yeah.
So equipotential lines are points where the where the electric potential is the same across the two plates, right?
Yeah, you can talk about the no. So it's a set of lines where the electric potential is exactly the same. All right. So for example, here, 0.5 volts, you can take any point, this point, that point, over there, point, over here, point. So everywhere potential is exactly the same.
Okay.
Potential difference between points, if you want to talk about the potential difference between any points on that surface will be zero, of course, right?
Yeah.
If you want to say about the potential difference, but usually people just say electric potential is constant, is the same. But when we are going to prove the perpendicularity of these lines, I will use the potential difference between points on the same equipotential lines. I will use that in that proof. Right. Yeah, but if you say about the zero potential difference, it's also absolutely correct. Right? Nothing wrong with that.
Yeah, thank you.
Okay, all right. So, and so now after introducing these very useful lines, now we have still one system which we need to discuss, point charge. So what's the expression for the electric potential created by a point charge? Now let's look at that system. So point charge, let's assume it's positive. Of course, it creates electrical ore, right? So the whole volume is filled with this electrical ore. And so now we can describe, of course, using we can describe that using either electric field or the electric potential. We want to introduce the electric potential. So we will take the probe charge, position it at the point where you want to find the electric potential. Let's assume it is at the distance r, right? And write down the expression for the potential energy. We have two charges interacting. Of course, in the previous lecture, we discussed the formula for the potential energy of 2-point charges. You remember, U equals K, product of charges divided by the first power of R. Of course, I didn't derive, but we discussed it. Okay, so now what do we have to do? We just need to remove this Q small probe charge. And what will be left, and what is left is our expression for the electric potential. Right? So again, that's the definition, V equals U over Q. So basically it allows us to remove Q small, which is the probe charge in this case. And as a result, that's the formula which we are going to use to find the electric potential created by a point charge at the distance r from the source of this, from the point charge which creates this electric potential. And again, you remember, since we introduced it from the electric potential energy, right? So of course we have to mention where is the reference point. The reference point is at infinity. When r goes to infinity, v goes to 0, right? So the electric potential becomes 0 at infinity. And of course, again, don't forget that charge can be positive and charge can be negative. If the charge is positive, so around the positive charge, the electric potential is positive everywhere, right? And goes to 0 at infinity. But if the charge is negative, then of course the whole electric potential around will be negative and 0 at infinity, right? Okay, then, yeah, so the reference point. Then what about the, yeah, probably first, the plot, three-dimensional plot. So for the positive point charge, you see, so we have a spike at the charge, at the place of the charge, and then it decays as 1 over r and goes to 0 at infinity. But of course, if you have a negative charge, of course, you're going to have like a spike, but in the negative direction, right? And then it will go to 0 at infinity. What about now equipotential lines? What about equipotential lines? Okay, in the equipotential lines, electric potential must be constant. So V must be constant. Okay, we assume that charge is given, so Q is given, K is universal constant, and we want to find lines where V is constant. So what should be, it can happen only when R is constant. When R is constant, V will be constant. So R equals to constant, some constant. So which line I'm talking about? R is constant. It's a circle, right? R is constant, it's a circle. So equipotential lines over point charge are circles. And you see this greenish, right? You see greenish circles on this picture. Or if we look from the top, right, at this plot, you will see something like this. So you see positive charge, and you see this greenish circles, right? So which are equipotential lines, which we use again to visualize the electric potential created by a point charge. Okay, so equipotential lines inside of a parallel plate capacitor parallel to electrodes. Equipotential lines over point charge are circles. Right, and now, so basically, yeah, that's what we're going to use, and of course the formula for the electric potential of a parallel plate capacitor. So that's what we're going to use most of the time. So now there will be, I think, question for you. Yeah. And it's in the chat. I created it around 8 a.m., but I saw you already chat a lot, so you need to scroll it. You need to scroll it up. Right. So the question is this. And there are two questions. So look for the conceptual test number 1, right? Conceptual test number 1 in this question, right? So what do we have here? We have a point charge, Q capital, of course, which creates an electrical aura, which can be described using the electric potential. So now we can describe that either using electric field or the electric potential. There's some noises. All right. Okay, doesn't matter. All right. Electric potential. All right. So, and we have 5 points: A, B, C, D, E. Which two points out of these 5 are at the same potential, at the same electric potential? The question is quite simple, but I like the follow-up question. So which 2 points out of these 5 are at the same electric potential? So the electric potential is created by a point charge Q. and I will just check your answers in the chat in my desktop. Okay, guys, right, so no, we didn't get to conceptual test 2. No. I see somebody already answered the question 2. No. So the conceptual test number 1, you see the poll, it's there in the test. I mean in the chat. Guys, it's not that complicated. Yeah, it's there, right? In the chat. Yeah, of course, it's not the most convenient because you keep chatting. Some of you answer questions in the chat, not through the poll. As a result, chat slides up, right? So, okay, so let's just discuss that. Okay, so of course, the electric potential is exactly the same if points at the same distance from the charge Q. Okay, out of these 5 points, there are only 2 points which are at the same distance, right? On the same circle, which is C and E, right? So obviously, so C and point C, right, and point E, you see, at the same distance from the point charge. So of course, they are going to be at exactly the same potential, right? But now the next question, which I like, and that's why so far this is kind of simple question. So I thought about sort of like dumping this question, right? But I like the follow-up question. So as I said, the correct answer is C and E. The next question, follow-up: which point or points have the smallest potential? I'm not going to poll that. All right, I will just give you 5 seconds to think, and then I will tell you usual answer and usually my response. So which point or points has the smallest potential on this picture? I'll give you just 5 seconds, right? Don't try to use the chat to answer. Right? Just think, and I will just discuss it. Usually, in a class, right, students pick point A, and they say point A has the smallest potential. It's partially true. Look, guys, on purpose, I didn't tell you if this charge positive or negative, Q. If this charge is positive, let's say 5 coulombs, for example, then your answer would be absolutely correct. So point A will have the smallest potential out of these 5 points, right? Because if charge is positive, you remember the maximum value of the electric potential at the point charge, and then it decays and goes to 0. But all the potentials are positive. Potentials at every point are positive. But if the charge is negative, Q is negative. Then, of course, we have a spike, but negative spike at the charge, right? So the electric potential everywhere is negative, right? And then the smallest, it will be the most negative electric potential will be at point C and E. So point C and E will be at the smallest potential if this charge is negative. And point A would be at the largest potential if charge Q is negative. I did it on purpose because, yeah, as every semester, usually students pick point A and say, yeah, that's the point with the smallest potential. But on purpose, I sort of forces you to make this kind of 50% mistake so that you would pay attention every time to the sign of the charge. Because in many parts of this course, you have to be careful and look carefully. Is this charge positive or negative? Otherwise, direction of the force or direction of the electric field will be different, right? So we have to be very careful about the sign of the charge. So that's basically the goal of this question. Yeah, because usually these students usually pick C and E without any troubles. Right? Okay, so now that's what I wanted to discuss, and now a few more examples about the equipotential lines or surfaces. All right. So, point charge, which we just discussed. I took this picture from the book, right? So this is our point charge, and look, electric field lines, which we used before, right? So you see these radial lines, right? And equipotential lines, like we just discussed, are circles. And again, you see what is the angle between these two sets of lines, or what are the angles between these two sets of lines? 90 degrees. As I told you, it's not by accident. In the previous, in one of the previous slides, we saw 90 degrees. Here, another example, 90 degrees. They are perpendicular to each other, right? And this charge is obviously positive, right? So you see electric potential is positive, right? Then, again, parallel plate capacitor. And even you see if we move closer to the edge of the capacitor, right? So you see electric field lines are distorted. So it's no longer, electric field is no longer uniform, but even there where the electric field is not uniform, still equipotential lines, which are green lines, right? You see equipotential lines and electric field lines, they're perpendicular to each other. Again, as I said, it doesn't matter how complicated your electrical ore is, set of equipotential lines and set of electric field lines are perpendicular. For example, like this, dipole. Okay, it's reasonably more complicated system, right? Positive charge, negative charge, exactly the same in absolute value. And you see red set of electric field lines, they start on positive charge and on the negative charge. And if you draw properly equipotential lines, you see these dash green lines. Again, it doesn't matter where, which point you pick for your analysis, every time these two sets of lines perpendicular to each other. Right. Okay, so there's just a few extra examples to emphasize on perpendicularity. So what's next? So now we know how we can find electric potential of a point charge, of a parallel, or inside of a parallel plate capacitor. But now, what if we have more than one point charge? What if we have 2, 3, 400 point charges? How can we find the net electric potential at a certain point? Principle of superposition. The same universal, powerful principle of superposition, which we used before, but now, look what we're going to get now. So let's assume that we have a few charges. Let's say Q1, Q2, Q2 is negative, you see, and Q3, for example, right? So what do we have here? This charge creates its own electrical aura. This creates its own, this creates its own. So we have superposition of three fields, right? Three electric potentials, right? So let's assume that we want to find the electric potential at this point P, the net electric potential at the point P. So we need to find contribution from this, then that, and this. And of course, we'll need to know the distances, R1, R2, and R3. And since the electric potential is a scalar function, we just need to add 3 numbers. All right? So we will have to, in order to find net electric potential, it's a V1 contribution from the first charge, V2 contribution from the second charge, and V sub 3 contribution from the charge number 3. And we derive just the formulas, because these are 3-point charges. So the electric potential of a point charge, it's a KQ over R. So KQ1 over R1. Then negative contribution from the second charge, because the charge is negative, minus KQ2 over R2. And then positive contribution from the third one. It's so simple. So of course, overall, you can use that for as many charges as you want. And I put this picture because now it's trivial. You remember how much we suffered in the first 2 recitation classes when we used principle of superposition for 2 first to find the net electric force. We just added 2 vectors. And the next recitation class, we tried to find the net electric field. Again, we just added 2 vectors, and we spent like 15 minutes diligently calculating everything. Now, in order to find the net electric potential, you just need to add 3 numbers. What can be easier than that? And that was the goal of to develop an alternative approach to analyze problems, to solve problems. So that's why we tried to move from a set of vector quantities to a new set of scalar quantities in an attempt to make our life easier, or life in physics and engineering, right, in research. Right. That was the goal, and now you see, it's so much easier. Okay, and so the next one, let's answer another question. Again, there is a conceptual test number 2 again in the chat, right? So there is a poll. Since you chat over there kind of a lot, so just scroll it up, right? I posted at around 8 a.m. today. Okay, so the next question. We have 2-point charges. One is positive, one is negative, the same in value. Basically, it's a dipole. It's a dipole. And we're interested at the midpoint. So this distance and that distance are the same. So midpoint between these 2 equal but opposite charges. So, of course, there will be some net electrical, or the value of the net. So there will be the net electric field at this point and net electric potential, because now we have 2 quantities which can be used to describe this electrical aura. You can use either electric field from the past, or now electric potential. So at this point, midpoint, what can you say about the electric field and the electric potential? And we have 5 options. Option A, electric field is 0, potential 0. Electric field 0, potential positive. 0, potential negative. E points to the right, potential 0. E points left, potential 0. Again, you just use the pole, right? We use it this way, like the 3rd class, I think. Right? Again, I agree that it's not the most convenient. Microsoft Teams should probably create, the poll should pop up sort of like separately, not somewhere in the chat, but that's how it works. Okay, let me look now. Okay, I see chat. I mean the poll 2. So most of you, 69% believes, keeps updating, right, in option D. No one believes in C. Okay. Option D, most of you pick 71%. Okay. Cool. Yeah, that's still the winning option. Yeah. Okay. Good. Right. So most of you believe that E points right and the electric potential is zero. Let's just quickly analyze. Let's start with the electric field. So contribution from the positive charge. You remember electric field lines start on positive charge, so and go away from the positive charge. So the electric field will point that way. Contribution from the positive charge. Contribution to the net electric field at the midpoint. And then negative charge will creates, of course, its own contribution. And of course, it will be in the same direction because electric field lines, they end at the negative charges. So that will be the negative, contribution from the negative charge. So both contributions are in the same direction, of course, if you add them up. So the net electric field will point again right. Again, every time I'm confused over here standing what is right, what is left, because I have a screen, okay, big TV in front of me, and everything over there is flipped. So sometimes I'm sort of losing orientation. Which side is the right side? Which side is the left side? Right. Okay, but that's for you. It's right. And so the electric potential. Okay, so the we just use principle of superposition, right? V1 plus V2. Of course, V1 will be a positive contribution, V2 will be negative. Since charges are the same, distances are the same, but this charge is negative, this charge is positive, right? So we'll have the same contribution, but one contribution is positive, one contribution is negative. So KQ over R, and the second minus KQ over R. So of course, they will be zero, right? So the net electric field is not zero, but the net electric potential is zero, right? And so if we look at the three-dimensional picture, right, as I told you, if the charge is positive, you see we have a positive spike, and potential around that charge is positive. But if we have a negative charge, then potential, we have a negative spike, and potential is negative everywhere around. But since we were interested in the midpoint, so this point, so of course, contribution from this is balanced by the contribution from that, giving us zero. Right? Okay, good. All right, so that's the answer. And again, quite often I give questions similar to this, maybe slightly more complicated among multiple choice questions on the exam. Now, okay, we still have a couple of minutes. Let me quickly do some integration. You remember, so now we know how we can find the net electric field if we have a set of point charges. But what if we have a charged ring? How can we find the electric field? You remember that problem. You remember how much time I spent integrating in order to get the net electric field at the point, at the distance z from the center of the ring. Right? You remember we used symmetry, right? We did some integration. It was kind of time consuming. Now let's see how we can find the net electric potential at the distance z from the center now. Okay, let me quickly, I think I should be able to finish it. All right. Let me switch to the whiteboard. Right. In order to impress, right? So turn off the green screen. Okay. Awesome. Okay, so this is our charged ring. Total charge of the ring is given. Again, the charge is distributed uniformly, radius is given, and we want to find the electric field at the distance z. Right, so that is R, this is z, and we want to find the net, the potential at that point P. So what do we do? Exactly the same beginning like 5 classes ago. We need to take infinitesimally small section of this ring. So of length dl, and of course that section will have a certain amount, small amount of charge dq, right? And since that is infinitesimally small, so we can treat it as the point charge, exactly the same beginning like I told you, 5 classes ago, 5 lectures ago. So we can treat it as the point charge. So, take dq and treat it as a point charge. You will see how simple this integration is. Point charge. So if it's a point charge, we can write down the expression for the electric potential at this point. It will be K dq over R, the formula which we derived for a point charge, right? So you remember, V equals K Q over R, right? So I just now apply for dq. And now we need to, and of course we need to write it in terms of what is given. So R, it's this, right? R small squared equals R capital squared plus Z capital, Z squared. So dq equals square root of R squared plus Z squared, right? And now let's integrate it. So V equals integral of dV over the whole ring, right? And it's an integral of this K dq over square root of R squared plus Z squared. So for now, I treat Q as the variable of integration. And look, K is constant outside. This denominator is constant, also can be taken outside. As a result, we're getting a trivial integral, K over square root of R squared plus Z squared, integral of dq over the whole ring. And what's the value of this integral? dq plus dq plus dq plus. You keep adding those dq's. When you go over the whole ring, what are you going to get at the end? The total charge. That's it. So as a result, the answer is kq over square root of R squared plus Z squared. You see how trivial integration is relative to what we've done 5 classes ago. And that was the beauty of switching to the scalar quantities, because everything life becomes brighter, right? Okay, guys, sorry for holding you a little bit longer, all right, 2.5 minutes, but I wanted to finish this lecture at this point. Okay, thank you, guys.